This problem is out of the book in section 5.1, and you have a velocity function in centimeters per second over a time interval from 0 to 4 seconds, and they gave that the function f of t is a straight line, as you can see graphed here. But before we talk about solving this problem, they ask for the change in the position, the exact change in the position. And I wanted you to note that distance traveled by an object is not necessarily the same as the change in position. It can be the same, but not necessarily the same. If over the journey the object is always moving forward with positive velocity, then the distance traveled will equal the same as the change in position, because you're going to be adding up distance constantly. You're not going to go backwards, and so your position will change from where it was at the start to where it is at the end. But if the object ever changes direction and goes backward, negative velocity, then that's when the distance traveled is not equal to the change in position. Because let's say you went out somewhere and then you turned around, came back all the way to the start. Your change in position would be 0, whereas the distance traveled would be a whole lot of distance traveled. So that's an example where they're not the same. So distance traveled is not equal to the change in position when you have negative velocity somewhere in there. If the object goes backwards entirely on the journey, then the distance traveled will equal the absolute value of the change in position, because the change in position will be negative, but it'll always be going one direction. So if you took the positive version of that change in position, that would be the distance, because distance is always positive. Okay, so what we're going to do to solve this problem is we're going to measure the change in position. We're going to do a rectangles. Rectangles are the right sum, and this time they're under estimates because the function is decreasing. And the green rectangles are the left sum over estimates. So we're going to find both those. Now, averaging these values will give a very good estimate of the change in position, as it always does. But in fact, since f of t is a straight line, you can see here that this green part, overage, cancels out with the underage exactly, so that really the areas under these curves, this straight line, will be the average of those two. So when you average the left sums, you get 12 centimeters. When you average the right sums, you get 4 centimeters. And let's just talk about that last moment where it's this -2, because the right sums are the red rectangles. So down here is -2, it's -1. So there is a height here of -2 over that 1 second interval. So you're going backwards 2 feet or 2 centimeters per second backwards. So your change in position is being affected by that. So it comes out 4 centimeters for your approximation of your right sum. You average those together, and it comes out 8 centimeters total change. Now let's view this another way. Here's another way of looking at it. We don't even deal with left and right, because we know how to get the area of this triangle here. And that's going to be the exact change in position. But the green part is going forward, and the red part is going backwards. The green area is 1/2 base. But I'll do that in green. There's the base. 1/2 base times the height. Okay, 1/2 base times height turns out to be 9 centimeters. That's the positive change going forward that the object did during the journey. But then the red area accounts for all the negative velocity, and that's 1/2 base. Oops, I want to do that one red. 1/2 base times this. On a rectangle, it's on a triangle, it's 2, but of course that will become negative position change. So when you're talking about area, you use positive numbers, but then you account for it in the story of the problem by saying, okay, so it's 1/2 base times height of the triangle. That's 1 centimeter. But then you say that's negative change, object going backward. So the total position change is the 9 going forward minus the 1 going backward for a total change of 8 centimeters. In actuality, the guy went 10 centimeters. He went 9 going forward and 1 coming backward, but the position change is only 8 centimeters. So here's the picture over here. The object goes forward 9 centimeters. Sees a stop sign, turns around, and comes back 1 centimeter, arrives at 8 centimeters difference than when they started. That's what's happening.